Yeah, I'm Andrew Jordan, and I've been at the University of New Hampshire now for almost 4 years, working on the Lunar Reconnaissance Orbiter. Another really interesting experiment is the Diviner Lunar Radiometer experiment. And a diviner, it's taken from the idea of a divining rod, where a man will take a stick out into the backyard and look for water, depending on how it wobbles. So it's a little tongue-in-cheek name. But what it does is it measures infrared radiation from the surface. So it measures the temperature of the surface. And it's this barrel right here. And the barrel can roll this way, and it can also twist this way. So it can aim in almost any direction it wants, which is pretty neat. And this is a map of the South Pole taken by it. And you can see, so the temperature runs from 40 Kelvin all the way up to about 200 Kelvin. It's some regions on the moon stay down around 40 Kelvin or so 40 degrees above absolute zero. And because the sun never shines in these craters, they're called permanently shadowed regions. So they are the coldest places ever measured in the solar system. Someplace in there, the coldest temperature measured was 29 Kelvin, which is amazing. And it's thought that there is water ice in these craters. We know there is water ice, at least in this crater right here. That's where the LRO spacecraft hit, when I was telling you about earlier, this Cabeus crater. We'll come back to this picture a little later when we talk about my research. There we go. The Cosmic Ray Telescope for the Effects of Radiation, or CRATER. It doesn't really study craters exactly, although now I guess you can say it kind of does. It's a bit of a misnomer. It studies cosmic rays. So mainly protons that are traveling at almost the speed of light. And there it is. It's a shoebox-sized instrument, so it's about this big or so. There it is, attached to the spacecraft. It's sort of like the hood ornament, like the Mercedes-Benz symbol stuck on the hood of the car, because that's the direction that LRO flies in. So some of the energetic particles come from the sun. So this is a coronal mass ejection. And coronal mass ejections can accelerate electrons and protons to really high energies. And that fuzz that you see at the end of this little video clip, the streaks and all the snow-like fuzz, those are those energetic particles exciting this. This is from SOHO, the Solar Orbiting Heliospheric, Solar and Heliospheric Observatory. Let's see, here's a really fuzzy one. That was a big event a while ago. But these events go off every so often. So I've been trying to figure out what effect they might have on the moon, especially in those really cold regions, because spacecraft traveling through Earth's radiation belt can actually be charged up so much that they get sparking. It's one of the leading causes of spacecraft failures. And so I've been wondering, could this happen on the moon as well? So those energetic particles can penetrate into the lunar surface. This is the regolith, or soil. I might call it regolith. It just means all the soil that's on the top of the moon that's been worn down by meteorites over the millennia. And it turns out that protons tend to penetrate just a little bit deeper than, electrons tend to penetrate just a little bit deeper than protons. Since that happens, in this cartoony example I have, there's a really strong electric field between the two, and there's no electric field above or below. But there could be electric fields above or below. I'm just showing the simplest picture. Now, these solar energetic particles, if they charge the regolith faster than the regolith can discharge them, so the regolith is slowly trickling electrons back up towards the protons to cancel out that charge, to cancel out the electric field. But if the SCPs are deposited in faster than the soil can discharge it, then the electric field increases and increases and increases. And if it gets to be strong enough, it can actually cause sparking in the soil. And this has been tested in the laboratory for a long time, almost about 100 years or so. It's well known. And the electric field that's needed is about 1 million volts per meter. And this is true of any type of solid. There is a bit of a range, but this is a good rule of thumb right now. The neat thing is that the colder the regolith is, the more charging you get, so the more likely you are to have breakdown. And in those permanently shadowed regions that I was showing you, here's a picture from the Lunar Reconnaissance Orbiter camera. You can see how all these regions are in shadow, and they always are. Some of these regions never see the sunlight and haven't seen the sunlight for over 1 billion years. So here's the temperature map. So I'm going to be concentrating on regions that are really cold, mainly. So again, there's that cartoony picture. And so along with a collaborator down at Goddard, he and I have put together a simple model that can predict the electric fields that would occur. So now I'm using not data from Crater, but data from the Advanced Composition Explorer. It's another NASA spacecraft, but it measures SCPs. It's between Earth and the Sun. So this upper panel that you see here, the black line, those are the protons, the flux of protons, and then that dashed gray line is the flux of electrons. And you can ignore this panel right here. This panel is the really interesting one. So these are the electric fields that we would expect to occur. So before the event, the electric fields are pretty much zero, and then they start increasing. And so E interior, the dotted black line, that's the electric field below the electron level. E surface is the electric field just above the protons up here. And then E gap would be the electric field in between here. And this gray bar that I've drawn in shows the region where breakdown is not expected to happen. So anytime the electric field gets greater than or outside this gray area, breakdown is a definite possibility. And so you can see that during this event back in 2000, I think this might have been the Bastille Day event, the electric fields probably got up to the point where in those permanently shadowed regions, you could get sparking all across the floor there. So it's thought that maybe in those, and this is a cartoon that I put together, there might be little random sparking events, only in the top millimeter or so of soil. I forgot to mention that the energetic particles only penetrate about 1 millimeter down into the soil. But if they're sparking, they might cause little poofs of material. So we've used Crater to look for these events. And so this is the threshold needed for sparking. And this is about 4 years worth of data from Crater. You can see that 2 events in 2012 surpassed the breakdown threshold. So it seems like even since LRO has been at the moon, there's been events that could have caused breakdown. And we're working with some of the other instrument teams to see if maybe they've found evidence that there might have been sparking, but it's kind of hard to do. But it seems like the regolith in those permanently shadowed regions may have experienced up to 1 million breakdown causing events throughout their history, because every year or so, on average, one of these events will occur, roughly more or less, depending on if the sun is more or less active. Recently, it's been really quiet. But on average, this is going to happen maybe once a year, and it'll affect things throughout about 1 million years. There's some other things that go into that calculation. So we think that it might have a significant effect on the soil in those regions. And here's some cartoons explaining that. So here's a soil grain that's been stuck together. It's on the moon in a permanently shadowed region. So if it sparks, if sparking happens, the sparking tends to go along the lines that are dividing the different minerals from each other. And this, again, has been seen in laboratory measurements. It's just the way it works. There's a strong electric field that's set up along those boundaries. So most of the sparking tends to occur along there, and that will tend to break the grains apart. So now we've got 3 grains instead of 1. They're much smaller, and some of them even have cracks in them, and those cracks are where sparks are likely to form later on as well. And so maybe this is a way of creating much finer grained soil in the permanently shadowed regions. And I'll get back to that idea again in just a little bit. And here's another cartoon. Here's a similar grain sitting on the Regolith surface. Dust grains on the moon are really jagged and crumpled looking. They're not the nice round grains like you see it in dirt or in beach sand. There's a grain. It sparks. The 2 little pieces can move away from each other. The sparking causes a little bit of vaporization, so it converts some of the material into a gas, and some of that will get deposited onto the surface of the regolith. And now the grains have been split apart, they've been moved. So that changes how porous or how dense the material is. It can actually make the material less dense. And that's what's seen with, and I didn't talk about this instrument, LRO LAMP, the Lyman Alpha Mapping Project, has measured ultraviolet light from stars coming into these dark regions, but then reflecting off the surface. And then the instrument detects that. So it's using starlight to look inside the permanently shadowed regions. And it does seem like the soil is fluffier than expected, and no one has really been able to figure out why that might be the case. So this is one possibility, that over the past million years or so, or even billion years, this repeated sparking has just kind of fluffed up the soil. So that was our trip all the way to the moon. And I got to show the picture view looking back towards Earth too. So thank you. Yeah, that probably depends on who you ask. Um, so right now there's a few scientists, or a number of scientists, who are, some of them work at NASA Ames out in California, and they're trying to put together a proposal, and they're going to apply. I don't remember who they're applying to, but they want to get NASA to send a mission just like that um, to a permanently shadowed region on the moon. But that's going to be quite a few years down the road, I think. It's a pretty small mission. And then I know there's a few private corporations, mostly in the US, as far as I know, that are also thinking about that. And I'm not sure where they are in their stage of getting to the moon. I think it's kind of hard because they got to get a lot of money to do that. But they are definitely interested in doing that. Like you said, it's a good place to go for mining. Oh, um,
Good
it
question.
would probably be near either the North or the South Pole somewhere. Um, and the reason for that is if you're near the pole, you can almost always see the sun. So solar power is really handy to have. So you want to be in a place where you can get solar power most of the time. So I didn't show you in those maps. Some of the regions actually are in sunlight for almost all of the time. So some of them are in shadow almost all of the time. Some of them are in daylight almost all of the time. So that's one reason to go to the poles. And then the other reason would be just because there does seem to be a lot of ice at the poles, and water is a great supply for drinking, but not just for drinking, also for creating energy. You can separate into hydrogen and oxygen. You can use that for fuel too. So that's the most interesting place so far. Most people would like to do it in these regions. Yeah. So in answer to your second question, yes, it could be tested in the laboratory. There's been one group that's done a little tiny bit with that, not very much. Um, and that's something that we want to get into as well. My group would like to do because we are getting involved with some experimenters. So stay tuned. You might have to stay tuned for the next few years. I'm not sure how quickly we'll have results, but that is something that I'm definitely interested in. So there are some magnetic fields on the moon, and actually, a lot of the moon is covered by magnetic fields, but just very, very weak ones. And some of the strongest ones are right here. You might be able to see this little lighter colored splotch just next to this crater right here. This is called Reiner Gamma, and it's a region of lighter colored regolith than anything that's around it. And there's a significant magnetic field associated with that. And there's some other regions, I think, out here. Um, then there's some on the far side of the moon. There's a lot more than I can remember. And they all have really strong magnetic fields associated with them, but they also have these strange shapes associated with them. They're called lunar swirls because they tend to be very graceful. And it's thought that the magnetic fields are actually redirecting the solar wind. So they have protons and electrons that are streaming from the sun all the time. It's thought that it might be redirecting the solar wind and causing um, these differences in the coloration of the regolith. The fields are strong, but we're not really clear that they're strong enough to keep out. They're definitely not strong enough to keep out cosmic rays. They might be strong enough to keep out the solar energetic particles, which have lower energies. Um, so that's actually related to what we're doing. We're not thinking about lunar bases, but we're trying to figure out what energies can be most affected by these magnetic regions.